So Bohr gave us this picture of the atom, where electrons could exist in specific shells around the atom, but they were not able to exist in the regions in between those shells. And we didn't really understand why. A worse problem with this is that if you have an electron that's orbiting in a circle like this, it should be creating a varying electric field. So it should be creating an electric field that's going up and going down. And this is very much our picture of light, and this is very much in line with how we consider light to be created. So if the electron is flying all the way around the outside of this orbit, it should be emitting light. And what that means is Bohr's model of the atom doesn't really fit with our current theory of how electrons behave, because what we should see is that this electron, if it was trying to orbit around it, would collapse to the nucleus very quickly, losing energy all the time as it produced light. So why are electrons only allowed to go in some spots? And why don't they emit light and fall into the center of the atom? Well, DeBroglie had a wave interpretation of this. He said, what if those electron orbits, or those allowed space, were actually standing waves that represented the position of the electron, and that the electron wasn't really traveling around in a circle like that, but that it existed in these standing wave positions, and it wasn't changing over time, but they were just like a standing wave on a string, just continuing to exist over the entire string. So first of all, let's make sure we remember what a standing wave is. If we have a rope, imagine it's tied to two walls, and we get that rope to vibrate, the vibration, if it matches one of a few key conditions, can continue to exist and grow and get bigger and be interesting. And if it doesn't meet one of those conditions, then it's going to basically cancel itself out quickly over time and stop existing. What do those conditions look like? Well, one condition looks like this. The next condition looks like this. The next condition looks like this. The shapes of these aren't really that important, but what is important is with these corresponding shapes, when a wave goes here and then is reflected back and then reflected back and reflected back as waves travel very quickly, the reflected waves always add constructively if we're going to be at the standing wave condition. So if we have these reflected waves adding constructively, they're going to get bigger and bigger and bigger. And as a result, we're going to get this substantial, big, important standing wave. If we imagine this in a circle, we can imagine then that if we want to make a standing wave pattern that looks something like this standing wave pattern, we can imagine a wave that's going to go inside and come back out. Maybe that's not the best example. Let's look at the next standing wave, because I think you'll be able to see it better. What if we made a standing wave that looked like this? Then that wave would go outside the orbit in one spot and then come inside the orbit in another spot and come back. And then when it repeated itself and went around again, it would go outside again and inside again and come back. And another path and another repeat and another wave that adds constructively in all locations. So this could be viewed as a standing wave for this atom. If that was the case, then we could imagine if this is one standing wave, we should be able to have another standing wave that looks like this, and that would be associated with a slightly larger orbit. That second standing wave, actually I'm going to make it simpler again because it'll be easier to see. It goes like that. So that second standing wave is now going to form two waves going around here. And so the idea here is that these standing wave orbits would exist if the electron had some kind of wavelength, And there would only be certain spots, just like there's only certain patterns on the string, where those electrons would meet that standing wave condition, and so there'd only be certain spots where they were able to exist or able to be in that place. What that means, though, is we're bringing back up the idea that electrons are now exhibiting wave-like properties. So over the past few videos, we've talked about light as it's behaving like electrons, and as it's behaving as a particle or a wave, the particle being photon, the wave being the wavelength, and other properties like that. And now we're coming to the idea that maybe electrons are behaving a little bit like a particle and a little bit like a wave in different situations. And this is where we start to think of the wave-particle duality. This is an interesting idea and certainly would explain why some radiuses would be allowed because they meet that standing wave condition, and while other radiuses would not be allowed. But it doesn't really address the problem completely because we're kind of using a two-dimensional interpretation of a three-dimensional object. So I'm going to pause here, and we're going to come back and talk about the Schrödinger atom and talk about how he solved this problem in 3 dimensions, and how by using wave predictions or wave behavior to describe what the electron is doing, he was able to make a mathematical model that agreed with the energies that were released when we observed atoms having electrons coming into those orbits.